So, sorry for that delay. Good morning, everybody. So, not really real time, as we are going to talk a little bit about today. Today's lecture will be about dynamic experiments, and that is really a source of massive data if you don't watch out. And so we got some literature, typical books, two new ones that you could look into if you're interested in this topic. So the Gostaby Image Registration Principles and Spatiotemporal Image Processing by Bernd Jehne. These are more targeted towards the time series analysis and the tools that you need for that. And there are also a couple of papers. One really good source of information on the technical side is the ITK registration guide. ITK is a huge library for image processing that was developed in the what's it called? Visible Human project, where they sliced, first of all, did imaging of one person, and then afterwards they even sliced him and made photographs of every slice. So it's really photographic and imaging based data sets. And in the context of this project, they built up actually a whole library, and that has been ongoing since, I think, the 90s even, that they have developed on this. And in that, there is also this registration toolbox, which is one of the most used, I would say. Little bit looking back, what we have done before. We're actually coming towards the end of these lectures. So we have looked at how we can prepare our images through image enhancement, also understanding a little bit of what's the features in the image. We also looked into automatizing the whole thing to make good workflows, looking at component labeling, looking at the analysis of single shapes, or also categorizing more complicated shapes and distributions. And last week we went into the topic of uncertainty and statistics, which is also a very important part when you talk about quantifying information from images. And last week I also brought up this quantitative big imaging, and today's lecture will actually be about producing a lot of data. Until now we have essentially only looked at having single images, or maybe a few images, or a data set of very varied data, but now it's about, in this case, producing lots of sequences of images which are somehow temporally correlated, and that produces a lot of data. If we do it in 2D or 3D, we produce even more if we do it in 3D images. We still need the variety, so these are the 3 V's of the big data. We still need variety to make a good statistical conclusion, and then in the end, when we produce all this data, we also need some velocity to handle it in reasonable time. So today I'm going to look again into a little bit motivation, some scientific goals of this kind of experiments, and looking also at how to simulate to prepare for the experiment, because if you're starting doing time series, it's maybe good to know before to how to design your experiment in order to get the information you need. So the imaging of dynamic experiments actually has 3 different components. First of all, we have a process that we want to observe, and it could be relating objects in motion, could also be characterization of some kind of continuous change. Could be that things are growing, shrinking, changing shape ratio, something like that. Can also be just changes in gray levels in the image. could be also how an increasing amount or decreasing amount of items in the image. So that is the process that we want to observe. Then we have the real-time aspect, and real-time is sometimes a bit strange defined, but in principle, what is about that we should be able to observe what's happening within the process while it's happening. And as a different side of it, you can also see the real-time definition for computing, and that is the data must be processed within the time of reaction that you need. And that means often when we're talking in computing that you should do the processing of data within milliseconds, and you should have a visual effect that it's happening immediately. So it's actually not always that real time means that you need to be really fast. It needs to be in the rate of the process that you observe. And usually you're not, for the analysis, you're usually not so interested in having it instantaneously. It's more important that you have it exact. And then of course we have the imaging part, where we have the capture, storage, manipulation and display of the images. And all this comes into the imaging of dynamic experiments part. We have different types of experiments when we are talking about dynamic experiments. We have continuous processes. So if you roll the dice, they roll and they stop at some point and they show some value. Then we have repetitive processes, things that coming back to the same point again and again. So if you have the swings, someone sitting there is going between two endpoints, and that is actually an effect that you can use in your acquisition, because you can, in principle, if it's very precise, you can use it one point as a trigger point, and then you can repeat it and sample many times and increase your statistics with that. One example, we looked at a two-stroke engine, which runs at, I think we did 8,000 RPM. And for us, a single image wasn't feasible. It would be essentially just noise. But by this triggering approach, we could actually get pretty nice images, because we could always accumulate every time it triggered. We got a little bit accumulation on our detector, and with that we could do a nice image where we could see how the oil distribution along the walls were in this engine. So there are different ways if you want to look at repetitive processes. So what kind of information are you looking for? You could, so often when you're talking about time-dependent processes, often quickly comes the question, how fast is something moving? Could be how many processes particles are present. So if you, for example, have a cell culture, you can see how the cell culture is growing over time. If something has a constant size, or maybe if you have some kind of fluid dynamic experiment, if some particles are moving faster than other ones, so you may have a central flow and you have some boundary condition flow, and then you can see, follow how that is. Maybe also how objects are rearranging depending on different conditions. So there are many questions you can ask in terms of time series experiments. And the questions that come up with image processing then is how can we first of all track objects from different time points? How can we track the shape? How we track the distribution, topology, and so on? And next question is, of course, also a little bit higher level question. How does these, say, technical identifications help you to answer your question? And well, that is for you to say exactly how you can do these things. But there are some pretty important topics from the previous lectures that we can bring in here. And well, I can do a wake-up call, so please maybe suggest something that we could use or need to do these things. What kind of preparation would we need to do of the images before we start doing these tasks? We can actually start already from the beginning. So often the images, when you do rapid acquisition, they are definitely noisy. So you need probably some kind of denoising, or at least noise-robust techniques. Next thing is, it would probably help to do some labeling. So that means we need to do some classification, segmentation to get the items. And then, of course, we run labeling, if it's component labeling or if it's watershed. That depends on how complex the image is. But these are the things that come back now, and we really need them in our toolbox to get to the next step. And well, here are some examples of what we have. So in this case, it's a foam that is growing. So this is a tomography of a foam. And in 3D analysis, if you do time series analysis, it soon gets pretty difficult to do it visually. You can, of course, look at this movie, see that things are growing a little bit, but you can't really tell much from it. So detailed things over the volume, like as I said before, if you have bubbles that are moving fast along the walls or in the middle, it's a bit difficult to see it here. So you really need to do an image analysis approach to tell anything. And in that case, we actually have a 4-dimensional data. If you really do a full 4D analysis, that's another question. Or if you can do separate, so you do first analysis of one, identify all the bubbles and their characteristics, then you go to the next one. Or if you would, for example, do a 4-dimensional filter that denoises with respect to previous and coming time steps. So that is also a design question and what the data actually requires. In some cases, you can do step-by-step 3D. Other cases, you have to do the full 4D. Some cases you can maybe, if you're really lucky, maybe even do 2D, but that's more questionable. Here are some other examples. So these are 2D movies, and the first one is a water jet, where you can, barely see the bubbles now, but there are some black dots flying across the movie here. The other one we have done here is coffee making. So it's actually taking this Mocha coffee maker, put it in the beam, and see how the bubbles or the water starts bubbling and how it transfers up to the upper container. And here I show a little bit of fancy visualization. So I actually display the movie as a 3-dimensional image, and then I can do cut planes and look at these planes, and you can see very nicely how the water is leaving the lower container and going up in the upper container, and these kind of ribbon-like structures, they are bubbles, water droplets on the lid. So this is a way how you can visualize 3-dimensional data. And sometimes it's good for the first qualitative assessment to do this kind of visualization. Another type of 3D data actually comes from the tomography, where we actually have to do a transform from the acquisition space, where you do projections around the object, and they are then reconstructed into a 3D volume. And that's a little bit a different, it's not really a time series, even though you can do time series with tomography. But that is also actually a pretty tricky thing. It's done in medicine, and that they have, for example, breath-controlled acquisition of the machines. So it's actually monitoring how the state of the breathing in order to have a stable, nice image. So that also requires quite some analysis and actually extra sensor input for the acquisition. Stage tilting is something more done in microscopy. It's kind of it's a limited angle tomography. So in principle, by wiggling the sample on the plate, you can get a little bit different views, and then you can get some depth information within the sample. So the scientific goals of dynamic experiments, these are just two examples, but rheology, looking how different liquids are mixing, or if there are items in the liquids, seeing how they're moving around. It could be blood vessel movement, a blood movement in the vessels, oil through a rock, and yeah, well, air going through dough when it's baked could also be a thing. Deformation is the other side, and we can actually go to sub-pixel resolution with the deformation analysis, really getting strain fields, coming to that a little bit later. And that is also a part that we can do with the time series analysis. And of course, there are many, many more applications, but some of them are these. When you do a dynamic experiment, you have to do a lot of planning also. First of all, you have usually a limited field of view. You have a voxel size. Also, your detector system has a maximum rate that it allows for doing the measurements at the given voxel size. And another thing, which when you in particular do X-ray, is that you have dose limitations, not only for patients in the medical imaging, but also if you go to a synchrotron and hit a delicate sample with the synchrotron beam, it may actually be damaged for radiation damage. And of course, with patients, you want to keep the dose as low as possible to reduce the damage effect of the imaging. Just as a comparison, a normal CT scan that you would do in the hospital, it way exceeds the limits that a professional is allowed to have on their dosimeter for a whole year. So it's very much X-ray dose that you get during a CT scan. And then it's a balance between what can we see and what will it help the patient to do this CT scan. And of course, there is always a non-zero cost for every measurement. So preparing a sample costs something, having the time on the beamline costs something, also, or whatever instrument you're using. And then you naturally have to go in the balance between the resolution you have and in space and in time. So maybe you want it extremely fast, but then you can only accept that you have centimeter resolution. Or else you need tiny, tiny details, but then you have to pull down the temporal resolution to match the signal to noise ratio that you would need. And of course, the factors that affect the image quality are, first of all, the process speed, how fast things are moving, the spatial resolution, and also the intensity dynamics, because at some point you don't see sufficient contrast to really detect what you can want to. And this picture from a little river shows actually the effect in normal photography. Up here we have the stones, which are static, don't move. You have a very clear idea of what they show. The water moving here, yeah, it's not so fast, but as soon as you go over the edge, making this little waterfall, everything is a blur. So that means we're not able to capture the structures of the water falling down. So we would have to increase the exposure time to get that. Would probably be possible, but in this case, photographic outfall effects, they want to have it blurry. So if we have, for example, dose-limited experiment, say we have 100 micron pixels, 1 second exposure time, and here I'm talking about neutrons, could be any kind of radiation that you would like to talk about. But anyway, you have these are the boundary conditions for what you get. If you want to maintain the signal-to-noise ratio and want to have smaller pixels, then you have to increase the exposure time. And vice versa, if you want higher frame rate, you need to increase the pixel size. So you can't have both. So what is usually happening is that to handle this faster region, you can do faster acquisition, but then you have to increase the pixel size, and then you get maybe a blobby pixelated image like this, but you may still be able to see the front that you want to follow. But of course, the fine details that you will see here, they are lost. But that is the kind of cost you have to take for this. And talking about frame rate, you need to do some certain amount of images along the change of the process. So this is in principle this is only a one-dimensional example, but here you have a rise of some process, so it's a stepwise with some smoothing. So it rises down here. Actually, it doesn't matter if you sample high rate, but as soon as you come into the transition zone, you want to have at least some points to be able to follow what is happening. And this one is, well, as I say, a good sample, decent sampling at least. And if you do the bad sampling, you would only have a few points, and you don't see at all what's happening in the transition. So that is actually what you have to look for and know about your samples, how fast you need to acquire your images. And some kind of intermediate solution, some processes you can stop, do your imaging, and then you move to the next level, and then you do your imaging. And that allows you to maybe so you drive the process to a certain level, then you can do 2-hour scan, and then you go to the next level, and then you do a 2-hour scan. Some processes allow it, others not. So this is like a technical solution to get the steps up when something happening. So if you, for example, can produce apply a certain suction or some voltage on your system and keep it steady, then that would be a possibility. But it is an approximation of the full step. So when you're planning your experiment, you can work along this triangle. You have feature size versus resolution, you have contrast versus noise, and you have process speed versus frame rate. And you have to move around in this triangle in order to find what suits your purpose the best. That is not that one is better than the other. It depends on what you need to know. So in principle, if we measure too fast, we may have sample damage. We may miss long-term changes, because if we measure fast, we produce so much data that it's not possible to handle it. And the data usually also are more noisy. If we measure too slow, then we may miss small and rapid changes. Also, the blurring and motion artifacts if things move too fast compared to the frame rate. And then going to the spatial side, to high resolution, then we may miss some unique structures because they move out of field of view because the camera can only take so many pixels, and if you have high resolution, your field of view naturally shrink. And if you go too low resolution, then you are not sensitive to small movements in the scene. So that was a little bit about measurement strategy. So let's move over now to the analysis, and a very trivial an analysis of a very trivial process. Let's say you have a bouncing ball, it goes up and down, following something. I model it here with a sine curve. In a movie, you see a dot that is moving up and down. Can use it, but it's maybe not so easy to analyze. Instead, if we view the movie as a three-dimensional volume, then we can do cut planes. We have x and y, they are the spatial coordinates of the movie, and we have time. So if we would cut a frame, for example, y, so a vertical coordinate, and time, then we would get an image showing the sine curve straight away, which makes it much easier to analyze. And this is something we used in this example, where we had a capillary rise experiment. So if you put a porous medium in water, it sucks up the water, and then you can see something like this. And not very exciting movie actually, but anyway, you see that there is a front going up. And if I look at the YT slice of this one, it looks like this. And with some image processing, I extracted the point of this front. And the measured points actually follow a straight line if you measure it as proportional to square root of t, which is actually confirming Washburn's equation for capillary rise. If you want to look into the full tutorial about this, I have it online, so you can just click through it, how I did the image analysis and all the steps, but I leave that out today. Another way is also looking at snowflakes. So would be, for example, if you have a wind tunnel and you have the particles flying around and want to look at them, there are different ways to do it, and usually you need to track all these particles that they have in the wind tunnel and try to make some sense out of it and then do some flow dynamic simulations. But in this case, I'm just looking at actually a synthesized movie of snowflakes falling down. Looks pretty relaxing. But anyway, it's a time series, and we have small dots, or dots that are growing. So it means that these snowflakes, they are moving a little bit towards us and slightly down. So what can we see here if we do it in a different way? So first of all, if we extract a first frame from the movie, it's just some dots. This color map is not ideal today's light conditions, but anyway, we have some dots here with different intensities. But what we often need to do if we have a time series analysis is we need to read the whole data set, and one part of the preparation is that you have this kind of reader function, because typically these file names, they are like snow underscore and some index number. So what we can do is we just put here some file masks, say in first and last image, and the output will then be a 3D matrix. And if we look at these, the first three slices of that movie, not so much difference because they are pretty slow, these flakes. But anyway, we have now the first one, which is called Snow 0001, 0002, and 3. So they are really indexed within the volume. And that's actually the first step, just to get the data in. And now we can look at this volume as a movie. Looking at it, we can see here, now I'm taking the image plane, or the the different planes of the movie and moving it as if it were pieces of a volume. And this is just a visualization, but it gets also a little bit an idea how you can analyze and work with the data. Another way is to actually project all the frames on top of each other. So here I did a max projection. I took the maximum value of all the frames for each pixel and projected like this. And all of a sudden, we start seeing actually that there is an interesting pattern in the data. We have more or less straight lines, not perfect. And we can also see that the general slope is here. We can see that some flakes are faster than others. So the slow ones, they are more or less a compact line. The faster ones, you see dotted lines. So you can really already read out from this one, qualitatively see some of the aspects of the image. And in principle, we can also confirm that the frame rate here is on the lower end because we have these dotted lines, and that says in principle that's undersampled. We can also do a full 3D view of the whole snowfall. So instead of doing this maximum projection, now I will show the whole volume in principle as a movie. And you can see how these lines are lying in 3D space, and then you can get even more information about them. So this is a way how you can do the analysis of the following the tracks of these. And well, when you start doing your experiments, you may also prepare a little bit, doing some simulations, seeing what sample rates. You could, for example, have this snowfall example saying that is a simulation of a real snowfall if you would look out the window and do some processing of that. But it gives you at least the boundary conditions, and many more complex of the complex experiments, they are often evaluated in simulations before they want to confirm that it actually happens like it is. And honestly, it never first time it never really confirms it, because the complexity of those experiments is so big that there are many factors coming in that you're not able to handle within a simulation. But it gives at least the ballpark in where you need to be. So, what do we want to start with? We can go back to our cell image, and we know the whole workflow now. We want to get rid of the noise, we want to get the shapes. We can see also if they're separated or to label them. And then we have some distribution characteristics. And now we want to do something out of it. And now comes a lot of different techniques that are used for the time series analysis. So we have some cross-correlation, we have digital image correlation. We can even do image correlation with physics combined. We can do transformations, geometric transformations, affine or non-rigid. And also what we would need to have is some kind of detection of features in the images that allows us to do some alignment in time. And these are the key points. So before the break, I would like to show just a basic simulation. Very simple process. We have these 8 dots. They are in principle already very simple. So let's see what they're doing. There we have it. So yeah, so essentially they're just moving up in the upper left corner. So we have a dx and dy equal -1. So nothing fancy, but it's a good starting point for seeing how an algorithm can work. So the analysis involves then the thresholding and the component labeling, so some shape analysis and distribution, and then putting everything maybe in a data frame because then we have the table form, which makes it easier to work with. And that would be that we have some code like this, where we do actually the labeling. In this case, we didn't have to do the thresholding because they were just black and white images. And then we get the region properties, get the centroid, the area, and the frame index. And all that is put then into this table, which we can use for the further analysis. And here is again something similar to the max projection I did before. So we have labeled or colored the different steps here with for the frames, and we can see which dots belong to which frame. And well, the motion that we want to find is this -1, -1 going up in the upper right corner, no, left corner, sorry. When we do the tracking with a simple case like this, we can actually go for the very easiest one, easy to understand. So what we are going to do is essentially just taking the nearest neighbor in the next frame and see if that is good. Of course, there are many more complicated methods to do it, depending on what your data looks like. But let's start with a very simple one. So we have a point in image 0, and we have a point in image 1. And then we just look for the smallest point in the next image. And that's about what we do in this example. So the first step is actually a bit expensive, but you actually compute the distance between all combinations of dots. And then you see that some are very long, some are shorter, and afterwards we just select the ones that have the shortest distance. In this case, it's actually a bit stupid because the distance is the same between all, or the motion distance is the same. So actually this point could have this and this as the nearest neighbor. Little flaw in the slide, but it could also actually happen in this ambiguity. And then we compute all the distances, and we can see what it looks like. We can even do a little visualization, a movie, showing stepwise how each point computes the distance to all the other. And then we can see the result, the first to the second frame, that all point up towards the left. The reason why it grabs it is pure ordering of the data. So that was pure luck that everybody are going in that direction. But anyway, and then we can see what happens if we run all of them, and we can see that it nicely actually follows and produces direction errors for all. But the problem is also, again, it's about sampling rate and how easy it is to track information. So looking at the upper row, we see here at low sampling rate, if you would take the next neighbor, you would take this one, maybe that one, and that one, and that one. So you would not really be able to grasp exactly the trajectory that you would expect. And in the real case, it would be the sine curve, so it would be like this. If you would increase the sampling rate, it would be much easier to follow the whole track. The only place where it's ambiguous is when they cross the roads. Then you can come into the trouble that they are actually grabbing the wrong one. And for that, we would need some smarter approach than just the nearest neighbor. And that's a good point to stop for break.